All right, so this was our example of a linear system, and we saw that we were able to solve it in two ways. Algebraically, kind of just guessing and checking, and then also graphically, we can see the solution where these solution sets are going to intersect. This is the only time it intersects, so this is the unique solution of this system. Okay, so let's get a nice definition for solution. Okay, so a solution is just a list So it's a list x1, x2, all the way to xn. So these are the variables of our linear system. Okay, and so you may see a list like this called an n tuple. Right? It's just a list of n things. If there were 5 things, we could call it a 5 tuple instead of just an ordered pair with only 2 things. Okay, so this is why it's a list. So a solution is a list like this of numbers. That makes each equation in the linear system a true statement. Okay, all right, so let's get some examples in. And I'm actually going to split my page in half down here so we can look at 2 things side by side. Okay, let's see if I can make this a little not blurry. There we go. Okay, so let's say we have this system, x1 minus x2 equals 0, and x1 minus x2 equals 1. Okay. All right, so we're just going to look at it and come up with some good solutions for each equation. All right, so it looks like 0, 0 should definitely work here. And also 1, 1 works. For the second equation, solutions could be maybe 1, 0, 2, 1. These things work. All right, and so I am going to graph these and see if I can come up with a solution for the full system. All right, again, this is my x1 and my x2 axis. Throw in some tick marks. Okay, so I'm going to plot the solutions for the first equation. We know this line, x equals y, or x1 equals x2. All right, and then I'm going to graph the solutions for the second equation. All right, so if I had drawn these lines perfectly, we would characterize these as parallel lines, and parallel lines never intersect. So what would be the solution of this system if these solution sets never intersect? Well, there would not be a solution. So we would say no solution for our linear system. All right, let's look at another example. Let's go 2x1 minus x2 equals 0, and then negative x1 plus 4 x2 equals 0. So you may notice something about this linear system and the connection or the relationship between these two equations, right? If you multiply the first equation by a -4, you're going to get the second equation. So let's see how that's going to affect our linear system. All right, so just eyeballing things for now. We'll learn how to actually solve these later with the system or with a process. All right, so 1, 2 will solve the first equation, also 0, 0. And in the second equation, 1, 2 and 0, 0 will solve the second equation as well. So we're looking at the same line here. All right, let's go ahead and graph this out. Don't need many tick marks here. Okay, so I will still try to use both colors. So we got 1, 2 and 0, 0. Solutions for the first equation. 1, 2, 0, 0. Solutions for the second equation. So both equations have the same solution set. So that means all of the solutions we get for each of them will be the solution for our system, which means we're going to have infinitely many solutions. And this is my shorthand for solutions. All right, so notice the 3 types. We've looked at 3 linear systems, and we've seen 3 different solution sets. This is all we will ever have. We will either have one solution where we have a unique solution. We could have no solution, or we could have infinitely many solutions. There is no in between. There are 3 solutions. Never. All right, so let's write that down as a note to conclude this lesson. All right, so here's our final note. A system of linear equations has, number 1, no solutions. Number 2, exactly one solution. And number 3, infinitely many solutions. There's no in between. All right, and so when we don't have any solutions in this first case, we say that our system is inconsistent. So in this first category, we're going to call this an inconsistent system. If we are able to find solutions, so if we're able to find exactly one, or there'll be infinitely many, then we call the system consistent. All right, and so that is the end of section 1.1.